Hello everyone, this is Kevin from ARM. Welcome to my session. So in the next 20 minutes or so, I'd like to walk you through the interrupt handling in Trusted Firmware M. The Trusted Firmware M is one of the open source projects hosted on trustedfirmware.org. It is a reference implementation of the PSA Firmware Framework M. The FFM is the specification for standard programming environment and the fundamental root of trust for secure applications on M-profile devices. The latest FFM is the version 1.1 extension. It introduces lots of new features, and including a new interrupt handling model. TFM has the initial support for this new handling model, and this is also the main topic of this presentation. Let's have an overview on TFM first. So TFM is the secure processing environment on M-profile devices. It consists mainly a secure partition manager and several secure partitions. Secure partitions provide secure services to both the non-secure processing environment and the other secure partitions. They are also responsible for interrupt handling. So a secure partition can provide both of the secure services and the interrupt handling, or they can only provide one of them. And they can divide it to PSA root of trust and application root of trust. The PSA root of trust is platform-specific implementations, and the application root of trust provides the application and product-specific secure services. So secure partitions are single-threaded, executing in thread model in an infinite loop that waits for inputs. The inputs are called signals, including secure service request signals and interrupt handling request signals. And according to different security requirements, secure partitions can have different privileged executions to have isolation boundaries between each other. Isolated secure partitions cannot access each other's data. And usually the PSA root of trust partitions execute in privileged thread mode, while the application root of trust partitions executes in unprivileged thread mode to have isolations. Okay, that's the secure partitions. So the secure partition manager, it is responsible for providing interfaces to secure partitions and setting up the isolation boundaries for secure partitions, and also scheduling secure partitions when they have new signals. Okay, that's the overview of the TFM. Let's have a look at the interrupt handling part. So the FFM divides the interrupt handling to two levels, like many other systems. So there are two handling modes correspondingly. First one is the second level interrupt handling, and the other one is the first level interrupt handling. So the second level interrupt handling, it is the default handling in the secure partition thread. So the initial handling does not really do the handling, but it is deferred to the secure partition thread. So this model is very easy and simple to use securely, because the handling is carried out in the secure partition thread. So there is no race conditions or concurrencies to take care of. But the handling is subject to scheduling. So the interrupt handling delay cannot be promised in some cases. For example, if there are some other higher priority secure partitions that are running, or the secure partition that handles the interrupt itself is busy with some other works, then there will be a huge delay after the interrupt occurs. So to solve this, and that's the only mode in the FFM version 1. So to solve the delay issue of the handling, the first level interrupt handling mode is introduced in FFM 1.1 extension. So the interrupt handling in FLIH is carried out right after the exception, the interrupt exception happens. So the interrupt handling can be carried out in a bounded time. But this is the interrupt exception context, which is not like the secure partition thread. So this handling cannot be, for example, blocked. So only very limited APIs are allowed and functionalities are provided. But there is a optional further processing to have more complicated interrupt handling. But this is optional. So if the initial handling, the first level can finish the handling, then you don't need to do the further processing. So basically, if your interrupt does not need to be handled in a bounded time, the SLH is recommended, right? Because again, it's simple and easy to use securely. You don't need to take care of concurrency things or race conditions. But if your interrupt do need to be handled in a very short time, then you should have to choose the FLIH. Okay, let's have a look into some details of the implementations in TFM. So firstly, let's look at the SLH. So the bottom half of the diagram here is the secure partition thread. It's executing in thread mode, and the top bottom is the handler mode. So when a interrupt exception happens, in this initial handling, the partition signal, the interrupt signal, is set to for the secure partition to handle this interrupt, and the scheduler is triggered. So when this secure partition is finally scheduled to run, it gets the chance to handle the interrupt. So yeah, I guess that's the SLH. And moving on to the FLIH. So before going to the implementations, let's have a look at some basic requirements. So to avoid evaluation of privilege on unprivileged secure partitions, the handling function of the FLIH, which is called the FLIH function, must execute in the same permissions as the secure partition who owns it and who is responsible for handling it. So this means the FLIH function must have the same privileged mode as a secure partition. So the FLIH function, the FLIH is also divided to privileged FLIH and deprivileged FLIH. This requirement actually applies to the SDH as well. But as the SDH handling is in the secure partition thread, so it naturally have the same permission as the secure partition. And the second requirement for FLIH is that the FLIH function execution must have the same priority as the interrupt exception. To ensure there is no lower priority exceptions can preempt this FLIH function because the FLIH function is designed to handle interrupts in a bounded time. So it shouldn't be interrupted by lower priority events. So bear these two requirements in mind, and let's see the implementations. So firstly, the privileged FLIH. This is a relatively easy one because the exception context is executing in handler mode, which always have the privileged execution. So the FLIH function can be directly called in this exception context in handler mode. And yeah, that's the privileged FLIH. Very simple and efficient for interrupts who needs to be handled in a bounded time. But the deprivileged FLIH is more complex. So as I mentioned, the handler mode always have the privileged execution. So to have a deprivileged execution for the FLIH function, an exception return to unprivileged thread mode is required. But doing this in the interrupt exception context will lose the priority of the execution. Let's take the simplest case as an example where the interrupt, there is only one interrupt to be handled. And so when you do this exception return in the context, in the handler mode here, the processor deactivates this interrupt. And then there is no active interrupts anymore. So this FLIH function will have the lowest execution priority, right? Just because there is no active interrupts anymore. Though this does not meet the second requirement of the FLIH function. So this model wouldn't work. So to solve this problem, this is the implementation in TFM. So the exception return to the FLIH function is carried out in the SVC handler. So when you do the exception return in the SVC handler, it is the SVC exception that is deactivated. And when you return to the FLIH function, there is still this interrupt to be handled, which is active. So then the FLIH function will have this have the execution priority of this interrupt because it's still active. Right. Of course, after the FLIH function, when you need to go back to the interrupt handler part, I mean here where the first SVC is called, you need to call another SVC to do the reverse works for the first SVC. And let's look at some details of this deprivileged FLIH implementation. So in the interrupt handler, when the interrupt exception happens, if the SPM decide it should use the FLIH function, it calls the SVC to prepare context for the FLIH function. So preparing context mainly means you need to prepare a state context on the secure partition thread, the stack of this secure partition. So the state context is the context that will be unstacked when you do the exception. So this is done by the processor. The processor will unstack the state context from the stack. So mainly it contains the 0 to R3, which can be used as the parameters for the FLIH function. But FLIH function actually does not have parameters, so they are set as 0. So then the linker register, it is where the FLIH function will return to. So when the FLIH function returns, it returns this to this linker register. So in TFM, we set this to the function that calls the second SVC to restore the context. So when the FLIH function returns, it does not need to explicitly call an SVC to restore context. So that's very convenient. And the return address is where the exception returns to. So in our case, it's the FLIH function. And the processor status register. As this is the actually, you can think it's whole new execution in the thread mode. So only the T32 bit is set. Okay, so that's the state context, and it is put on the top of the secure partition stack, right? And then the second thing in the context preparing is the isolation boundaries. If there is the need to switch isolation boundaries, you do the switching in the preparing context part. Yeah, and also as the state context is on the secure partition stack, you might need to set the current PSP to the top of the state context. Okay, then you are ready to do the exception return. So when you when the exception return happens, the PE on stack from the PSP you have set of this state context to form a initial execution environment for the FLIH function, and the stack goes back to this state without state context, and the FLIH function executes in this secure partition the stack. Because the stack actually is part of the isolation boundaries. So that's why the secure partition stack is choose for the FLIH function. Yeah, and then when the FLIH function returns a SVC, another SVC is called to restore the context, which is mainly the reverse work of the preparing context. For example, to switch back the isolation boundaries if there was a switching, and yeah, switch back the PSP if there was a switch is set up on the PSP. And there might be other works, some other reverse works. So And after cleaning up the context, that is to actually restore to the state the context where the first SVC is called. So this process does not change any registers or any stack pointers. So yeah, that's the interrupt handling should be right. The interrupt handling shouldn't kind of damage the original execution. And then the interrupt handling is done. So exception return, and it's done. And as I mentioned, there is a optional further processing of the FLIH because the FLIH function is executing in a very special context. So you cannot do everything. So there is a mechanism for secure partition to have some further processing in the secure partition thread. So this mechanism is very like the SLIH, if you remember, or if I go back to the SLIH slide, right? So it's the same. Sets the signal for the partition, trigger the scheduler, and waits for scheduling. And this is optional, so the FLIH function will return a value to the SPM to tell the SPM if further processing is necessary. So this return value is carried over through the R0 of the SVC, and the SVC handler will get the return value and it knows if the further processing is necessary, is required. Okay, I guess that's all from my presentation. Thank you. Thank you for attending.